All right. Well, hi, everyone, and welcome to this second or last day of our drinking one. Okay, okay, there we go. All that jazz out of the way. So today is going to be on chlorination. This is the last day of the math. We're going to be spending our time with working through chlorine questions and going through some examples of stuff that'll help you with other stuff. Chlorination is just the start of chemical addition. Obviously, if you are a treatment operator, you do fluoridation, phosphate addition, alum addition, you do some lime softening and so on and so forth, or ion exchange softening. But the parts per million equation is the equation that can be used for every single one of these, all right? Today, we won't be interrupted either. I'm not going to have someone knocking on the door telling me to vacate the premises because of COVID stuff like yesterday. I'm at home today, so that won't be happening. So with that being said, if this is definitely the chapter where you're going to see everything come together. So if you have any questions about stuff, please do ask, raise your hand or put in the question. And if it's something that Mike can't answer, he can go ahead and ask me. No, it did not, James. I guess I could just say no. That'll go away. All right. So with that being said, let's go ahead. And I think, 51, we were at like 52 yesterday. So we're pretty close to everyone being on at this point. I'm going to say, go ahead, Mike, and run the first poll question so that we can go ahead and get started when that's completed.
Great. Thanks, Scott. Yep. So that poll question is up. Appreciate everyone participating in that. This is our standard run-of-the-mill first poll question here. How many folks are viewing this webinar at the location you're at? So we'll give it a minute or so. I don't know what Matt usually does, but I keep my little dad joke Holy Bible here. So to fill the void, why do hamburgers make poor witnesses? They won't talk no matter how you grill them. So that's what I got for you this morning as we kind of get started and answer this first poll question. So we've got about 90% participated. Just a reminder that if you do want CEC credit for today, this is how we're tracking your participation. So if the last few folks, if you're sitting there and you want that CEC credit, make sure you log in there. But we've got about 94%. So I'm going to go ahead and close it up here, Scott, and hand it back off to you.
All right, let me minimize this thing so this goes away. Okay, all right. So with that being said, let's go ahead and get started on the first page today. All right, so you're going to see this is known as concentration expression, okay? And concentration expression today is going to be chlorination, but it is named concentration expression for the fact that you can do fluoride and alum dosing and the whole 9 yards with this formula, all right? So don't be alarmed when you see that. That's just kind of what it is, okay? So the reason why it's called parts per million parts, okay, it's because you're doing one part into a million parts of another thing. So the thing we're dealing with here is we're going to be dealing with 1 pound over 1 million pounds. And yes, this is going to be that big M's unit that we've talked about, okay? So I just want to revisit with that big M unit and big million gallon and million pounds unit, just that unit only. So once you find that unit and use it for the calculations, you can go back to 2 decimal places, but we're going to want 3 decimals with this, okay? And I'm going to show you why it's really important to have 3 decimals with this very first off here. Okay, so pounds of chemical is typically used if you're doing stuff as like dry compound or something along those lines. Just getting a general concentration. That's commonly used for like dry alum feeding. You can use just pounds of chemical. But the thing that we're really going to be looking for is we're going to be looking for, coming down here further down the page, we're going to be really looking for that pure chemical, okay? So the parts per million equation today that we're going to be looking at, I'm going to be writing it like this, okay? Cl2, okay? And I'm writing Cl2 because that is pure chlorine. That's what chlorine is when it's pure. it is Cl2, all right? So I'm not going to write pure chlorine each time. You're going to be seeing me shorthanded as Cl2. And then this will be over million pounds of H2O, okay? And I put the number sign here. It's not a hashtag, it is for number, okay? This isn't Instagram or Facebook or whatever you hashtag in. It's going to be just, this is a number placeholder for million pounds of water. And as you can see here, we see the big M, okay? So I'm going to be showing you how we get that big M unit, how we do it pretty straightforward. So this is why it's parts per million though. It's because it's pounds of chemical over million pounds of water. So part per million parts. All right, and the million is going to be the bottom there. So on top of that, let's start to think where we live. Do we live in Canada or Mexico or no, we live in the United States. So I'm going to cross this. Don't cross this off, but this I'm going to cross off, okay? All right, we're not going to be doing chemical dosing based on like international or metric standards, but we do need to know that parts per million and milligrams per liter are equal to each other. These are equal, okay? That is an equal sign. So if I have 5 parts per million, how many milligrams per liter do I have? Well, that would be, yeah, you guessed it, that would be 5, okay? So I'm just giving you a heads up that milligrams per liter and parts per million are the same thing. So with knowing that, you can see both of these sometimes being used in the question, okay? So don't be confused if you see them both. It's because they equal the same thing and they mean the same thing. Does that make sense? All right? And no, I'm not going to give you milligrams and liters on an exam and expect you to figure it out, okay? It's not. If anyone's told you that, it's a lie. It's not true, okay? But we could use, you know, if I'll show you an example, I think today, if we have time to get to it, where milligrams and parts per million are used both in the equation, okay? So, well, without further ado, let's get into chlorine questions. And so 1 pound of chlorine and 5,000 pounds of water equals what concentration milligrams per liter? So right there, we're asking it as milligrams per liter, but parts per million and milligrams per liter equal each other, so it doesn't matter, right? So if you remember the parts per million equation, it's parts per million equals, well, pounds of Cl2. Well, I know that this is 1, and it says million pounds of H2O. Well, I don't know, but I do know that I got 5,000 pounds of water. So I need to get that to this unit because what it currently looks like is just like this, 5,000 pounds. You don't see that big M unit, okay? We need to get it to that. In order to get it to that big M unit, you simply divide it by 1,000,000. That will transform it to million pounds, just like that. Okay, so I'm going to go ahead and put the 0.005 here, and then it's just 1 divided by 0.005, which if we do that, we're going to get 200. So 200 parts per million, which is the same as milligrams per liter. But one thing I want to show you, okay, so I said this unit specifically right here, big M, needs 3 decimal places, and we got 1, 2, 3. So if I only went to 2, let me show you what would happen in this, okay? So if I'm taking this number to 2 decimal places, what would I round that to? Well, I'd look here and I'd round this one up because it's 5 or greater, so you round up. So I'd get 0.01, right? A million pounds. Well, what is 1 divided by 0.01? It is 100 parts per million. Excuse me, I don't know what the heck's going on here. Okay, so I have 100 parts per million. So if you're doing a certain disinfection type method that calls for 50 parts per million, 200 parts per million, so on and so forth, you could actually be cutting your dose in half based on a rounding thing, all right? So that's going to be a big problem. That's why we can't do that, okay? So we need to go to the 3rd decimal place with rounding on the million pounds because you won't throw your dose off that much. And I'm going to tell you, legitimately, if you're working on disinfecting like, 6-inch, 500 foot, small pipe, even at 500 or 600 foot of pipe, yeah, that seems like a lot. But to be honest with you, the amount of water that thing actually holds and the weight of the water is not that significant. So if you go to the second decimal place in a small pipe like that, you may be going lower than what is required to disinfect that water main. All right. So that's why I strongly recommend that you go to the third decimal place on the million pounds. I can't hear the audio because can everyone else hear me?
So we haven't gotten any other comments about that yet. So Mark, if you want to try and check, make sure your speakers are correctly plugged in. I hate to be that guy. How about I need to put my own little microphone down. I know if you click the little caret top next to the to your audio, you may be able to choose if you have headphones plugged in. It may be trying to go through your computer audio. I'd say worst case scenario, you may want to log out and log back in.
Right.
If you still have a couple issues, feel free to send in another Q&A, and I'll see what I can do to help.
Okay. All right. So with that being said, we want to make sure that we go to the third decimal on this unit only. Okay. Only on the million pounds. I don't care anywhere else. And the matter of fact, once you're done with million pounds, like once you've used it in a calculation, you can go back to 2 decimals, but it's when you're using it in a formula like this, it needs to be 3 decimal places. Okay. So with that question done, I want to go up here to the top of this. So I know, look at that, sample problems already. Huh. Okay, and I'm going to give you a couple pointers on stuff. So we're going to cross this off first off. Okay. So the parts per million equation is something that a lot of people struggle with sometimes. Okay. They struggle with like, how does it work? It's algebra. It's lots of work. Well, there's that's always a thing of the past, right? So there was something on the first day. I don't know that was in the homework. I don't think so. But there's something that I want to teach you. I'm going to teach you some algebra. Oh boy, here we go, right? Everyone goes, algebra. You can keep your algebra and send me some lunch. But I promise it's not too bad. We'll say like that, okay? So I have 3 over x equals 9 over 21. Okay, this, you see how we have 2 fractions that are set equal to each other, right? So doing the math on this may not be so easy. Everyone looks at it and goes, oh yeah, I don't really know how to do that. Well, there is a simple trick. There's an algebraic way to solve for this, and it's called cross multiply and divide. Okay, so you go like this. You cross multiply. So you do 3 times 21, which is 63. And then you do 9 times x, which is 9x, right? Kind of like that. So that's what we got. We got 3 times 21 is 63 over here. And then 9 times x is 9x, okay? So we cross multiply. That was pretty easy, wasn't it? Okay. And now you need to divide each side by 9. And, I would say 63 divided by 9 is 7. So x equals 7. Okay, well, that wasn't too bad. Could I make it easier? Well, let me show you another one. Let's go 4 equals x over, we'll just go with 10, okay? Well, is the 4 a fraction? Well, yeah, it is. We learned that any number can be over 1, didn't we? So can we do cross multiply and divide here? Yeah, absolutely. We can cross multiply. And kind of like this, right? So 1 times x is x. And what's 4 times 10? So that's x equals 40, right? Well, that was even easier, wasn't it? It didn't even have the cross multiply and divide. Okay, what's the point? Why am I showing you this? Okay, well, let me show you this. What happens if I wrote I wrote 4 parts per million equals X pounds of pure chlorine. So I'm looking for pounds of pure chlorine over 10 million pounds of water. Does it make it any different than this one? It doesn't. Just because I put labels there doesn't make this any different. You literally, this is over 1. You just cross multiply the thing like that. So you got 40 pounds of pure Cl2. That's how you solve for this, is you just cross multiply the two when you insert them, okay? And this is how you solve for pounds of pure chlorine given the parts per million equation. You literally, parts per million pounds of H2O, you just cross multiply the two, you get it. It isn't, there isn't any big trick to this, is there? It's not that bad. So there is no big trick to that. One other thing I want to caution you of is 2 different scenarios here. So I have 200,000 pounds or 0.2 million pounds. Okay. This is a bad example. Let me retry that. How about 7 million or 7 million pounds? That's a better example because it relates to number 1 here. So when we're looking at a problem, the first thing you're going to need to do is you're going to need to find pounds, right, in a question. And remember, it has to be in million pounds. So my question to you is like a number 1, 5 pounds of chlorine and 7 million pounds of water equals what concentration? So is that 7 million like this, or is it 7 million with the big M like that? Looking at this, which one do you have? Well, in this one, you have this. And you can tell whether it's in pounds or million pounds by looking for all the zeros. So if you don't see a bunch of zeros behind it, like we don't here, then that means it's 7 million pounds already. It's already in that big M unit. How do you get to that big M unit? Remember, you divide by a million. Okay. So if it's not in million pounds, you divide it by a million to make it into that. And the other thing I have, if you have gallons, what should you do? You need to convert to pounds. Remember, we talked about this yesterday. To convert gallons to pounds, you just multiply by 8.34, okay? And then don't forget, pounds, you got to get to million pounds, you divide by a million, all right? So with me telling you that, I'm going to give everyone like 8 minutes to do page 55 and 56. You can see there's more sample prompts here. And then we'll go over them, all right? So I'm going to give everyone 8 minutes, and then we'll come back together to do these. All right. Looks like it's been 8 minutes. So 5 pounds of chlorine and 7 million pounds of water equals what concentration in parts per million? So if I look at this, I look here, I don't see all the zeros. So I'm already in that million pounds unit. So I'm going to have 5 divided by 7 here, which is going to equal 0.71 parts per million. All right. 5 pounds of chlorine and 200,000 pounds of water equals what concentration in parts per million here? All right, so I have 5 over, well, this is not million pounds. You see all the zeros here? So in order to get this million pounds, I got to divide this by a million. And it's going to give me 0.2 million pounds. So now that that's 0.2, do I need to add all the zeros behind it though? If it's only zeros for decimals, you don't need to add them, okay? You only need the 0.2. So the 0.2 here is going to give me 25 parts per million for that, okay? 6 pounds of chlorine and 15,000 gallons of water equals what concentration in parts per million? So I have 6 pounds. I know that much. Well, 15,000 gallons. What's wrong with that picture? Is that million pounds? It is not. Well, I need to get gallons to pounds first. Multiply by 8.34. Gives me 125,100 pounds. Now, how do I get that to million pounds? Well, I'm going to divide that by million. Gives me 0.125 million pounds. So 0.125 million pounds goes there. Which gives me 48 parts per million. Okay. So number 4 looks a little bit different. How many pounds of pure chlorine must be added to 900,000 gallons of water to produce a residual of 2 parts per million? So this one looks a little bit different. So I'm going to tell you, in most chlorine questions, we're going to give you, are going to have parts per million, all right? They're not going to be like these ones up here, actually. They're going to be more similar to this. So the first thing we're going to do is we're going to convert, or we're going to take the 2.0 parts per million and put it into our equation immediately. And then it'll be pounds of Cl2 up here, and then million pounds of H2O. I recommend, and you'll see as we start getting into this a little bit further, I'm going to be adding that into the questions immediately, all right? Now I need my million pounds of water. Well, I have 900,000 gallons of water. Is that pounds? No, it's not. So I need to get this to pounds. So we multiply by 8.34, and that's going to give me 7,500,000 and I don't remember if it's 2 or 6. Hold on. 6. 7,506,000 pounds. All right, so how do I get this to the million pounds unit? Well, I got to divide it by a million. And I will get 7.506 million pounds. So 7.506 go here, 3 decimal places. And 7.506 times 2, because remember when it's like this, all you do is you cross multiply. So I got, when you cross multiply those two, I got 15.01 pounds of Cl2. All right, on the next page here. 3 pounds of chlorine and 7 million pounds of water. So 3 over, where do I get my million pounds from here? Well, I'm going to have to divide my 7 million here by 1 million, right? Like this. And that'll give me 7 million pounds like that. So the 7 will be 3 divided by 7, which is something at 0.43 ppm. All right, 10 pounds of chlorine in 100,000 pounds of water equals what concentration in parts per million? So I got 10. Do I know how many pounds of water, a million pounds of water I have? No, I have 100,000 pounds. So what I need to do to that? Divide it by a million. Well, 10 divided by 0.1 is 100 parts per million. All right. 42 pounds of chlorine are added to 4 million gallons of water. What is the concentration of chlorine? So I know that I have 42. What do I need to do to this 4 million first off? Well, it's gallons, so I need to get it to pounds by multiplying by 8.34. $33,360,000 pounds. Well, how do I get 33,360,000 pounds to million pounds? You just divide it by 1 million, right? And this will give me 33.36 million pounds. So divide 42 by 33.36. And I get 1.26 ppm. All right, one more before we move on to the fun stuff. All right. So I'm going to tell you, if you haven't quite noticed, one of the things that's been a reoccurring theme is right here. We're looking for million pounds. Million pounds has been a reoccurring theme, hasn't it? Here and here and here and on the other page and the other page. I mean, the million pounds has been a reoccurring theme. So to be honest with you, that is going to be common practice. The million pounds of water is going to be one of the very first things you need to find in any chlorine question, okay? I know it's a reoccurring thing that we've seen so far. Well, it's a thing that's going to continue to happen. So I have 1 pound of Cl2 here. I'm going to put it in 10,000 gallons of water. Well, I need to get gallons to pounds, so 10,000. 10,000 times 8.34 gives me 83,400 pounds. I need to get that to million, so I need to divide it by a million. As you can all see, divide that by a million, and we're going to get 0.083 million pounds. So I need to divide this 1 by 0.083. And I get 12.05 parts per million. There's a dot there, my bad. 12.05 parts per million. All right. So that's kind of an introduction to the parts per million equation. I promise that they're going to get harder.
Hey, Scott, can I ask a clarifying question before you
Yep.
flip that page? So the question asks, what's the concentration in milligrams per liter? And you listed the answer in parts per million. I know you talked about it earlier, but just clarify, those are equivalent, correct?
That is correct. Milligrams per liter and parts per million are the same thing. And to be honest with you, I think of them the same thing too. So for calculation purposes, thinking of them as identical is 100% okay. The only time that you can't get away with writing them as parts per million is on doing reporting, like some of your MOR stuff and some of your end of year sampling reporting requirements. They'll specifically say milligrams per liter, but parts per million and milligrams per liter are identical. I know it says that, but the same thing is that since it equals it, it's no different than just saying 12.05 milligrams per liter like that. It's the same thing.
Yep. Awesome. Thanks
They're
so
one
much.
for one. All right. All right. So this isn't such math involved. This is kind of explaining to you what chlorine forms exist. Okay. So first off, with chlorine forms, there are three main types. And, I should clarify this. There are three main types of free chlorine. Okay. There are three main types of free chlorine. Okay. So this is the chlorine, the different chemicals used for adding chlorine to chlorination. All right. There's chlorine gas. Chlorine gas is the first one that we're going to talk about. Okay. So first off, chlorine gas is yellow in color. Okay. It's yellow in color. And it's a couple other things about it. It's heavier than air. Crap, heavier than air. And it's very oxidizing and harmful. So what I mean by harmful is if it like explodes, it's very harmful. Like it can kill you. Okay. So chlorine gas is the first chemical known to be used for chemical warfare. It was used in World War I by the Germans. It's not used for that now. And to be honest with you, it's not the most common form of chlorine used for disinfection now. Okay. In part because it's, can be very deadly. So it comes in 150-pound cylinders and 1-ton cylinders. Typically, a 1-ton cylinder is maybe 3 foot in diameter and maybe 10 to 12 foot long, somewhere in there, about for size, to just visualize it. It's not as big as you would think. I just finally saw one for the first time like a little while ago because I've always used bleach anywhere I've done stuff. So I saw a 1-ton cylinder. It wasn't as big as I thought it would have been. All right. But chlorine gas is very oxidizing. And what I mean by that is it can eat stuff. There is a water plant in Michigan that bleach and hydrofluorosilicic acid were accidentally mixed by a chemical delivery. It mixed off-gas chlorine, and the chlorine gas, because of it, it required mandated mandated evacuations from surrounding neighborhoods of that water plant, and the water plant completely got eaten. It went through, the chlorine gas went through the plant, ate all the electrical systems, cement walls, everything. It went through and ate the whole plant and wrecked it. It was like a $36 million rehab project to rebuild the water plant after that. Took 2 years and 36 million, something like that, to rebuild the water plant. And that's here in Michigan. So chlorine gas is nothing to mess with, all right? It needs to be self-contained in a room that has ventilation to evac it out if something's going wrong. Typically, what we got here? I don't know if I'm allowed to talk about that, James, to be honest with you. Do some research. It happened in 2011, all right? Yeah, I don't know if I'm allowed to say what city. I don't want to throw anyone under the bus, so to speak, in that. But that did happen here in Michigan in 2011. Okay. So, yeah, it's very bad stuff. And to be honest with you, the only places that are really still using it are your larger water systems. And that's because chlorine gas is 100% available. It's 100% pure. Okay. That's something else to know. This is 100% available chlorine, because it does exist in gas form. So like if you get these and you like a 150-pound cylinder and it's leaking a little bit, you use an ammonia puffer and you kind of puff it and it makes a white smoke to see if it's leaking. And usually if you tighten the lead washer, because they use lead as the washers on those, it'll like stop leaking. It's not a guarantee, but it can happen that way. All right. So calcium hypochlorite is the next one. Calcium hypochlorite is 65% available chlorine. That means if you were to take a, say a box of it like that, right? And we say this calcium hypochlorite, we would agree that, that's half the box. So somewhere right around here, all this down here would be available chlorine. 65% of whatever the substance is considered chlorine at that. All right. So the other thing about this is a white crystalline powder. They also exist in pucks. Okay. So the pucks that, if you have a pool or know someone has a pool, or you've been to Walmart or Meijer, or I guess most people I think are from Michigan here. So Walmart or Meijer, you've seen those pool pucks, or, 5-gallon buckets full of pucks or whatever. And that's what they are. That's calcium hypochlorite, just so you know. It goes by a common name of HTH. All right. I can't say there's not many who use this for disinfection. It's mostly okay, good for that. It's mostly used in distribution systems because there's a lot of kick, or it's pretty easy, it's stored in a 5-gallon bucket. And if it's used in distribution systems, what they do is they glue it to the bottom of the main. When they're disinfecting it, they fill the main and pressurize it and give it adequate time to dissolve before they start the chlorine disinfection process. So it is used by a couple municipalities. I heard Detour Village, when I was up in the UP, matter of fact, uses them in an erosion type feeder, which that's what you would use to feed them. I was just surprised that a municipality actually uses them. I hadn't heard of a city that used them, but there is some, evidently. So sodium hypochlorite, this is liquid. This is what everyone knows as bleach, right? This is AKA bleach. The thing about it is bleach varies. It goes from 3% all the way to 19% available chlorine. The typical that you're going to see is 10 to 12.5% strength at cities is typically. But if you're doing like on-site generation, that's where you get the low 3%, where like you dump a bag of salt into a generator and make your own on-site. This is the most common form of chlorine. All right. This is the most common thing that's ever used. And to be honest, it's a straw colored, if I could write, it's a straw colored liquid, right? It isn't clear. It's a straw color. It has a little tinge of tannish or yellow or straw that we refer to it. It's the most commonly used. All right. It does not mix well, obviously, with acid. If it mixes with your fluoride acid, it will off gas chlorine. Okay. So that's not something to mess or mix with by accident. And then it brings me, so these are the three types that we'll be dealing with, right? You have bleach, which is 3 to 19%. You have the white powder, which is a solid 65%, or you have gas, which is 100%. So everything we've been dealing with now, we've been assuming so far has been just gas because it's pure. And I want to talk about one other one real quick. I want to talk about combined chlorines. And what combined means is it isn't a free chlorine or free hypochlorous ion floating around in the water. It's chlorine combined in some fashion. And the one that's most common, or the only one that's used in Michigan at the moment, is called monochloramines. Okay. This is where chlorine and ammonia are bonded together, and they are disinfectant out in your water distribution system. Okay. These have a couple uses for them. They are long lasting in the distribution system. They're long lasting. So if you have a very big distribution system, like the city of Lansing uses chloramines, and their distribution system runs from DeWitt all the way down towards Holt, which is, 20-ish, 5-ish miles. And east to west, it runs like 15 miles. So it's a fairly large distribution system. Well, monochloramines are long lasting, meaning you still have a residual far out. It doesn't just kind of disappear at dead ends like free chlorine does. Some of you who've sampled for chlorine know that at your dead ends or low stagnant areas, you have low chlorine levels, but you don't have this here. It's long lasting. It fights biofilms. All right. It helps attack biofilms because of its long lasting ability. And it has another thing. It doesn't form disinfection byproducts. Okay. This is another added bonus to this, byproducts. So that's another reason. So at your dead ends, you'll still see chlorine levels, and then you won't have your disinfection byproducts, which are formed, which are THMs and HAA5s. Okay. So you have your THMs and HAA5s are disinfection byproducts, and these do have MCLs associated with them. This is 80 parts per billion, and this one is 60 parts per billion, okay? That's the MCLs for them, okay? These are known carcinogens, and they form by chlorine and organics reacting. Jeez, if I could write. Okay. Disinfection byproducts are formed when chlorines and organics in the water react with one another. Sample the dead ends. Dead ends, yeah, whatever. Okay. We won't be seeing any calculations of chloramines, but I just want to throw it out there what they are used in Michigan. There isn't a whole lot of plants that use this. Some of the Detroit plants, Ann Arbor, Lansing, are really about the only ones that use it, but it is something that exists. It is something out there. Oh, and it's 25 times less efficient, I guess is the way of putting it, as free chlorine. So you have to run a higher residual of this stuff because it's 25 times less effective than free chlorine for killing stuff. Yes, it doesn't form disinfection byproducts, but you have to increase your detention times and all that stuff for it to do its killing, if that makes sense, because it's 25 times less effective. All right, I don't know. I'll give you guys a minute to write that. I guess there's a lot that I wrote down there. All right. I think that's probably adequate. All right, let's go ahead and get moving on this stuff. All right. On a particular day, a treatment plant applies 150 parts per million, 150 pounds of chlorine, and the flow meter shows that 2 million gallons of water were treated. How many parts per million were applied? So I know that I have 150 pounds of chlorine, but I got to convert 2 million gallons to what? Well, I got to get it to pounds. So you multiply by 8.34. $16,680,000. How do I, yeah. How do I get that to million pounds? Well, you just divide it by a million. And that's going to give you the 16.68 million pounds. So 16.68 here, million pounds. So 150 divided by 16.8. And it's going to give me 8.99 parts per million. Okay. So you got to be careful with reading these types of questions, what you're given and what you have. All right. So we had 2 million gallons of water. Well, I had to get it to pounds and I had to get it to million pounds in order to do the question. All right. A chlorinator is set to feed 10 pounds of chlorine per day to a flow of 250 gallons per minute. Okay, so I kind of already told you, right? The first step is finding million pounds of water, right? We've kind of already seen this, but it comes from one of three places, right? It is given amount, a flow rate per time, or it's a volume. Well, so far, everything we have seen has been a what? Has it been a flow rate, a given amount, or what has it been? Well, it's been a given amount, correct? 2 million gallons of water, like in the last example, or a couple 100,000 pounds of water, like it was in the first few that we did, right? Or we sometimes get a flow rate per amount of time. So let's look. 10 pounds of chlorine per day at 250 gallons per minute. So we got to get this to days, don't we? So this is where unit conversions are going to come back to play. I got to get gallons per minute to pounds per day, okay? So I'm going to convert my gallons to pounds first. I know that 1 gallon, gallons are on top, gallons have to be on the bottom. So I have 8.34 pounds here. All right. I have 1 minute. Well, if minutes are on the bottom, that means they have to be up top to cancel. Well, I need to get to hours because then I need to get to days. This will give me my pounds per day. That cancels. Yep. Okay, and once I have pounds per day, I can then convert to my million pounds, right? So I got equals 3,002,400 pounds. Excuse me. How do I get that to million pounds now? Well, you got to divide it by a million. 3.002 million pounds. So I have 10 pounds of chlorine over my million pounds, which is 3.002 million pounds of water. So you see how we had to step through and convert to get our 3,002,400. Well, I got to get it to the million pounds. Divide. Because like I said, it's going to be one of these three ways. It's going to be find a volume, it's going to be a flow rate per time, or given. Given is obviously the easiest one, right? These both require math and conversions, whereas this one just might be one-step conversion. So now that I got the pounds of chlorine over my million pounds of water, I do the math. And I got 3.33 parts per million. That example. All right. All right. One more, and then we'll take our break. All right. A community chlorinates its water. So first off, you can cross this because this is not how we're going to do this stuff. You can cross this baloney off. A community chlorinates its water. 1.7 million gallons are pumped each day. How many pounds of 100% available? Okay, now you're starting to see percents. If it's 100% available, what are we talking about? Is it gas? Is it powder? Or is it liquid? Although powder was 0.65, the liquid was 3 to 19%, and gas was 100%. So it's gas, all right? So now I want to teach you one extra thing that we're going to be doing here. How many pounds of 100% available are needed to produce 1 part per million? Okay, so you see how we're giving you the 1 part per million. Whenever I read a chlorine question, if I see that, the very first thing I do is immediately write it into my equation. So I will write out my parts per million kind of like this. As soon as I see the parts per million, I put it into my equation just like that, okay? So I want you to get in the habit now, because most of the chlorine questions we're going to see are going to be given a parts per million like that immediately. Okay. So then you'll have your pieces of the puzzle kind of like you have to find your million pounds, right? Well, now that I have my parts per million written in, I have to find my million pounds, because I told you that that's how it is. And it's either given volume or flow rate per time. So do you see a given amount here? I do. I see 1.7 million gallons. Is that already in the big M unit? Well, do you see a bunch of zeros behind it or numbers? No. So this is already 1.7 million gallons. Well, how do you get that to million pounds? How do you get gallons to pounds? Multiply by 8.34. That million unit will stay when you multiply by 8.34, okay? $14.178 million pounds. This converts to pounds. The million stays. All right. Now, where does that go? Well, look at your equation. Where does it go? It goes right here. And what did I show you do when you have it right there? Well, this is over 1. You just cross multiply the 2. So you're going to need 14.18 pounds of Cl2. Because when you multiply those, that solves for that. Okay, given that it is 9:31, I will see you back here at 9:41 to resume after break. All right, so 10-minute break, guys and gals. All right, everyone. Well, we should be getting back from break now. It is 9:41 there. I guess I'll go ahead and share my screen again. All right, so we should be getting back now. It's 9:41. So we are about to move into the real chlorine calculations now. I mean, we've been doing some, but we're do a couple more things with some chemical stuff real quick. That's like the last piece of the puzzle. And then we're going to be doing chlorine questions. All right. And I mean, there's enough chlorine questions in the back of this that I might forego like the last example and jump right into doing calculations with you guys and having you work through some, okay? Because I have found that sometimes works better. All right, with that being said, Mike, you want to go ahead and run the next last poll or second poll question?
Yep, thanks, Scott. So that should be on your screen right now. If you want to take a second and answer that poll question, did you attend math sessions 1, 2, and 3? I know it's been a week for a handful of you, so I appreciate you all jumping on with us this week, and Scott for our fearless leader here running the charge. Thanks again for everybody participating this week. So, and just a reminder, if you do want participation credit to earn those CECs, make sure you answer these poll questions. So I know people are just getting back from break, so we're going to let it kind of run for just about a minute before we wrap it up. But thanks again for participating. We've got about 85%. We had about 92% answer the first one. So if for whatever reason you're having some issues with answering that question, or if the poll didn't pop up, feel free, put something in the Q&A for me so that I can see that. I'll go ahead and document that so that when we go through and issue those CECs, that we've got that record there for you. So I think with that, we're over a minute here on this question. Scott, I'm going to go ahead and wrap it up and kick it off here.
All right. So, well, welcome back from break. Was much, I don't know, maybe much needed, maybe not. You're definitely probably going to be looking forward to the end of class once the chlorine starts here in the next couple pages. All right. So, all right, this is like one of the last things we got to do, and then we are good to go to the chlorine questions. All right. So, first off, how many pounds of chlorine are in 4 pounds of a compound that is 65% available chlorine? So we're gonna go like this, cross this off, okay? Because I'm gonna show you what I taught you the first time, and then it would be so that I don't go out of my way of teaching stuff, okay? So we have 4 pounds of a compound, right? So we're saying that we got 1, 2, 3, 4 of them. We'll just say we got 4 pounds of it, right? This is the pound. And we got 65% of each one. That's somewhere, like this or something. Is chlorine. But what's the sum of all those? Is there a way we can mathematically do it? So would you agree that we're going from a compound to pure, right? We have 4 pounds of a compound. Well, in this case, it's HTH, or calcium hypochlorite, right? Because it's 65% available. So we're saying how many pounds are in 4 pounds of calcium hypochlorite, essentially. Well, the first thing you're going to do is you're going to go like this. We learned to always convert percents to decimals, right? So this is going to give you 0.65. So to go from a compound, so if you are starting with and you're going to, you simply multiply by the percent. So we had 4 pounds of it. You multiply by the percent. This converts it to pure. That's why I spent that time explaining to you what percent was, okay? Wasn't a waste of my time. It was a reason for it. So we have 2.6 pounds of Cl2. Okay, I want to let you know this is done maybe 5% of the time. It's not very often that we go from compound to pure, okay? So on the next example, I'm going to show you is what we do mostly. But I'm going to give you like, I'll give you a minute to solve this. How many pounds of chlorine from 10 pounds of a compound that has 65% available chlorine? I'll give you a minute to solve this one real quick. How many pounds are in 10 pounds of a compound? And it's 65% available. Right? 6.5 pounds of Cl2. That's not so bad, is it? That seems pretty easy. But here's the kicker. As I said, this is what's only done about 5% of the time. This is the minority here. Let me show you the majority of what you're going to be doing most of the time. Okay. So first off, we'll just cross all this baloney out here and this too. Okay. There's another example right here. If we calculate that we need 9% or 9 pounds of 100%, so we need 9 pounds of pure, but the only thing we have is those pucks, right? Or powder. Provide this concentration. How many pounds of the 0.65 do we need? So this time you're given a pure number, right? You're going to compound. Because most often people are using bleach. It's not very often people use gas. So if we're using bleach or this powder, we want to know how much of it we're going to need. So if I got 9 pounds of it and I got 0.65, to go from compound to pure, we multiplied. So what's the opposite of that? Divide by the percent. So you're going to divide the 9 by the 0.65. And when you do that, you get 13.85 pounds of compound. So I want to point out, we will be dividing majority of the time. Okay. We'll be dividing by the percent majority of the time. So this is going to be the method that you're going to be using the most. Okay. Well, so how does all this relate in a chlorine question? Is typically where we go from here. All right. And what I want to do is I want to turn to page 64. And I want to show you number 3 here in the sample problems. Okay. I know there's an example, but the problem I have with examples is everything's written right there. So as I write it and explain it, it kind of makes no sense. You're like, oh, okay, sure. Whatever you say. Okay. This is a true chlorine question. As in, this is what you can expect to see on exams. This is what you can expect to see kind of in a real life scenario. Okay. So let's get started with it. I'm going to walk you through the steps of doing this. And then we're going to do some more. We're going to spend like the next hour on doing chlorine calculations and real ones, not fake ones. It's not to say what you did was fake. It's just to say that it wasn't It wasn't everything. How about that? So how many pounds of calcium hypochlorite, 65% available chlorine, would be required to disinfect 800 feet of 8-inch water main at 50 parts per million chlorine? Okay, so the very first thing I'm going to do is I saw my 50 parts per million and the equation. So I'm going to write it out. And then I'm going to write out my whole thing, pounds of CO2 over a million pounds of H2O. All right. So you see what we've done so far. I've used that number and I've put it right here, because what this does is this gives you kind of like a roadmap. All right. So the next thing we need to do is find this. And I told you one of three places. It's a given amount, it's a flow rate, or it's find a volume. Which one do we have? Flow rate, given, or volume? Now I see a volume right here with 800 foot of 8-inch water main. So the thing I need to do to 8 inches first is what? I need to convert that to feet. So that's 0.67 feet. Okay. So volume, this is a cylinder, is 0.785 times diameter times diameter times the length. Okay. So if I stopped right here, I would only have cubic feet. But I need pounds. How do you get cubic feet to pounds? Well, cubic feet to gallons is 7.48. This is gallons. And then how do I get the pounds? Gallons to pounds is 8.34. So yes, I am going to type that all into my calculator. That equals 17,000, oh boy, 17,586.40 pounds. Well, how do you get 17,586.40 pounds to million pounds? How do we get that to million pounds now? I divide by a million. That's going to give me 0.018 million pounds. Now that I have million pounds, where does that go? Well, where does million pounds go? Right here. And when you have million pounds in parts per million, how do you solve for pounds per? You just cross multiply. So 50 times 0.018, and this is going to give me 0.9 pounds of CO2, which is pure chlorine, okay? That's not what the question's asking for, though, is it? It's asking for calcium hypochlorite. So the last step is to go from pounds of chlorine to calcium hypochlorite, and you divide by the percent that you convert, 0.65. This is 1.38 pounds of calcium hypochlorite. Yeah. 1.38 pounds of calcium hypochlorite. So it's been a journey. It's been 4 days, right? Very first day, we talked about percentages and then conversions. Second day, we talked about volumes. There's not really a whole lot in here that comes from the third day because that's kind of its own thing. But then today we talked about making million pounds, talked about parts per million, and we talked about here. But you can see there's your percent that we from first day. Here's your calculate or formulate or unit conversions from first day. Second day, here's your volumes, and here's the fourth day stuff all added together. So in order to get the chlorine, that's why we started where we started. All right. I often get asked, well, why do we start with this? Well, If it's not obvious at this point, then I don't know what to say. You know, it's literally everything. Don't forget, convert inches to feet. Okay. So with that being said, we're going to turn the pages back here. It's page, if you haven't realized, there's a bunch back here of extra chlorine calculations. I want everyone to go to page 60. Don't lose 60. Don't lose this because you're going to want to use this as a reference. Because page 68, I want everyone to do the third one down. So page 68, third one right here. I'm going to give you all like 4 minutes to do or to attempt this, and then we'll go over this together. Okay. So I'm going to give everyone 4 minutes to do this one right here, page 68. And then we'll go over it. And this one is identical to the one we just did. Process wise, obviously some of the numbers are different. All right. How'd we do? All right. Calculate how much HDH powder in pounds, 65% available, will be required to obtain a chlorine dose of 75 parts per million in an elevated storage tank. So first, before I even finish reading this, I'm going to go and write my 75 parts per million equals pounds of Cl2 over a million pounds of H2O. All right, and then go back here, 75 parts per million elevated storage tank that has a diameter of 45 feet and a depth of 70. So first off, I see the word diameter, so it is a cylinder. I got to find the volume of it. So 0.785 times by 45 times 45 times 70. Well, I got to get it to gallons and I got to get it to pounds. Times 7.48 times 8.34. All right, so I'm going to show you one other thing here now. 6,941,612. I know there's decimals behind it. Okay, I get that right there. But why didn't I write them? Okay, well, I got to get this to million pounds. So what happens when I do this? So I'm going to get 6.942, right? 6.942 million pounds. Because when I switch to million pounds, I need third decimal place, which is going to be this one I'm going to be going to. You can see that when you divide it. So I didn't really write the other decimals because when I divide by million, those ones are going to go away anyway. So just FYI, when you're doing the pounds, when you're going to convert to million pounds, you can just simply leave the decimals off if you want, because when you divide by a million, they're going to go away anyway. Okay. So 6.942 goes there. Now what do you do? Well, if it's there, you just cross multiply. So 75 times 6.942 is going to give you 520.65 pounds of Cl2. I need to divide that by 0.65 now to get it to HCH powder. And this gives me 801 pounds of HCH. Okay. How do we do? Did we get 801? I mean, this is why I know like all but two of you recommended this to be online, but this is where I wish I could be like, people see, like I can see faces and people like the light bulbs go on, or and I'm just like, yes, I got it right kind of thing. But you know, it is what it is. Okay. I want everyone now to do this one. How many gallons? All right. So what I want you to do first off is if you got something to block it with or whatever. I got this. Okay. I want everyone to do the question just like this one to this part and then stop. Okay. So do it just like you just do the other ones, but ignore the last sentence for now. Okay. Just do what you're doing. Do all the way to here. All right. I'll give everyone like 3 minutes to do that. So now we should be getting a little bit better. All right. So just do the question just like you did this last one, but ignore the last sentence for now. Okay. Don't worry about the assume. Just stop the question mark and do all the steps to like right here. All right. I give everyone 3 minutes to give that a go. All right, it's been 3 minutes. All right. So how do we do this one, right? Well, I told you this one is just like the one above it, right? For the most part. All right. How many gallons bleach? 5.25% available required. All right. See, 50 parts per million again. So I'm going to write it over here in my equation. 50 parts per million equals pounds of CO2 over a million pounds of H2O. Kind of like that, right? Now I need to find my million pounds of water. Required chlorine 500 feet of a new 6-inch water main. Okay. So divide this by 12. Get 0.5 feet. Volume for this is 0.785 times 0.5 times 0.5 times the length of 500. Now I got to get it to gallons, and then I got to get it to pounds. So do it all in one step. 0.785 times 0.5 times 0.5 times 500. 7.8. 8. So I got 6,121 pounds. Remember, I told you don't have to put the decimals because when I divide that by a million, they go poof anyway. They disappear. Let's see my calculator here. I got 0.0006121. So 3 decimal places is going to give me 0.006 million pounds. So I put the 0.006 right here. Now what do? Well, you cross multiply, right? This way. And that's going to get me 0.3 pounds of Cl2. And now what do you need to do? Well, you need to divide by the percent. So 0.0525. And you got 5.17 pounds of, in this case, it's bleach. Okay, now this is what makes bleach different than the calcium hypochlorite or the powder, right? It says, how many gallons of bleach will there be? Or how many do you need, essentially? This is where this last sentence comes in. Assume that bleach weighs 10 pounds per gallon. Well, if I'm going to assume that it weighs 10 pounds per gallon, then what do? This is my conversion factor you need to get from pounds to gallons, okay? So, the last step to do, so everything you've seen, it's all the same, right? Volume, over here, cross multiply, divide by percent. But now I need to get to gallons. So you take how much it weighs and divide it. So 5.71 divided by 10 will give you 0.57 gallons of bleach. That's the only difference between what you did here and what you did there, is for the fact that it talked about giving you gallons of bleach. All right, well, that doesn't seem too bad, does it? All right, well, let me look through these real quick. Is there another? Well, I want to go to that one too, but. All right. Let's try the last one here. I'll give everyone, I want to give you like 4 minutes real quick on this. And then Mike, can they all chat in the chat? Like all the individuals, can they say yes or no in the chat by chance?
No, they cannot, but I can turn that on real quick if you want to.
Yeah, so I want to give everyone like 4
Okay.
minutes if they can. And then when I go through it, I want people, if you will, after you go through it and I go through it, I want to see, just like out of curiosity, how many people are getting the right answer, okay, or very close. So yeah,
Okay,
if you
cool.
can, we'll give them 4 minutes to do this question. And then if you can turn on chat, I want them to try to chat with us just to see.
Yeah, so I have it set up. So now, folks, you should be able to go into the chat function in your Zoom toolbar, and you can send something into hosts and panelists. So that'll go to Scott and I, and that way it just is Scott. You'll be able to see everything that people submit.
Yeah, so give you 4 minutes, we'll
Cool.
go over it, and then you compare your answer to mine, and we'll see how you guys did, okay? Unmute myself real quick, and then let's go ahead and go through this. All right, So how many pounds of calcium hypochlorite, 65% available, would be required to disinfect a 1,000-foot main, 12-inch, blah, blah, 50? Okay, well, the 50 is the first important part here. 50 parts per million pounds of Cl2 over my million pounds of H2O. Okay. So I got that. Now I need to go through here and figure out where my million pounds of water are going to come from. Well, they're going to come from right here. So I got to convert 12 inches, right? So volume's going to equal 0.785 times 1 times 1 times 1,000. My diameter is 1, 12 divided by 1 foot, times it by 7.48 and 8.34 to get it 2 pounds. So I got 48,970 for pounds. Now, to get that to million pounds, I need to divide this by million. 1.049 million pounds. So I'm going to put my 0.049 here. Now what do? You cross multiply. So 50 times 0.049. I promise after this question, I'm gonna teach you, I'm gonna show you another question on the next page that's actually gonna teach you guys some more stuff. Okay, so when I multiply those, I got 2.45 pounds of Cl2. Now I need to get the pounds of calcium hypochlorite, so I divide by the percent. Divide by 0.65, and I'm gonna get 3.77 pounds of calcium hypochlorite. Okay, so you can just say yes or no, just out of curiosity. I want to see how people are doing. So let's see, you got 1.377. Can I get some yes or no's? Did you get the right answer? More than the 3? Yes, yes. Okay, well, that's good. I'm glad to see that, because so what I'm doing and showing you has worked. It has sank in a little bit, huh? That's good. That's good news. Okay. Alex, I'm sorry to say, but your name looks very familiar. And it's because I scored your exam app the other day. That's the reason why I remember your name, because I was like, oh, that's an interesting name. So, okay. All right. Well, now that, okay, what do I got? I got to have a question. Yes. All right. Mike Stolly. I know that name too for some reason. All right. So here on page 69, okay. On page 69, I want to show you guys something new, something different, right? Because we feeling good about chlorine. That's the thing. I want people to feel good about this. And the thing about it is, to be honest, fluoride and chlorine are very, very, very similar. And a lot of the chemical stuff is, right? You got to know the concentration, the parts per million. And if you know the flow rate or something like that, you can figure out how many pounds or whatever are going in it, right? Okay, so the one I want to talk about is on page 69. It's this very first one here, okay? Maybe I should do the one above it first, because that one's a little bit different. Okay, let's do this one first. This one, we're going to do this first. We got time. We will do this one, and I will explain it to you. Okay. It is desired to apply 3 milligrams per liter of chlorine to a well, which pumps 500 gallons per minute. How many pounds of chlorine gas are used in one day? Okay. So milligrams per liter is the same as what? Parts per million. Okay. It's the same as parts per million. So I'm going to have my then pounds of Cl2 here and my million pounds of H2O. Okay. But I need to figure out, where am I going to get my million pounds from? Well, this one's different, right? I told you it comes from one of 3 places. It's a given amount, like 500,000 gallons or 500,000 pounds of water. It's a volume, which we've seen in the last 3 questions we've done, last 4 questions we've done, or a flow rate. Okay, so we have a flow rate in this one, don't we? It says for 1 day. So I got to figure out how many pounds per day this is to get my million pounds. So I'm starting with 500 gallons per 1 minute. So I got to get gallons to pounds, right? And how do we do that? Well, we've just been multiplying it by 8.3, but that's because 1 gallon equals 8.34 pounds, kind of like this, right? That part's done. Now I got to get minutes to days though. Well, minutes to days would be minutes to hours. So 60 over 1. If you think about it, then I got to get hours to days. If hours are on the bottom, where do they got to be to cancel? Up top. Well, there's 24 hours in 1 day. Okay. This will get us our pounds per day. The reason I'm doing this is I'm showing you that flow rates can show up sometimes too in these, okay? And this is a flow rate one. What? I think I did something wrong. 500 times 8.3 times 24 times 60. Nope, I'm doing something wrong. I'm just 6,004,800 pounds. How do I get that to million pounds? Divide by million. 6.005 million pounds. So that 6.005 is going to go right there. So 3 times 6.005 gives me 18.02 pounds of CO2. And this says gas. Gas is 100%. So this is done. 18.02 is gas. That top pounds of pure chlorine is essentially you're finding for gas chlorine when you do that. So any question that asks you for like pure chlorine or gas chlorine, that's it. It's just find your million pounds, you cross multiply the two like we have been, and you're done. Okay. So for future reference, gas or pure, if it says 100% pure or gas, you're like, yes, because it's way easier. All right. All right. So we need to talk about this one. This is the only one in this packet that's like that, but I want to show it to you because it's a little bit confusing. All right. A water supply has a chlorine demand of 3 parts per million. Oh, well, that's not parts, that's just milligrams per liter. It has a chlorine demand of 3 milligrams per liter. It is desired to maintain a residual throughout the distribution system of 0.4 parts per million. Hold on a second. That doesn't really change anything. How many gallons of bleach, 12%, are required to maintain this residual, knowing the water supply pumps 300,000 gallons per day? So it's not a very big place. And it weighs 10.4 pounds per gallon. Okay. Now, first off, I have 2 different milligrams per liter and parts per million here. They are the same thing. The question is, how many of these do I need to add to my thing? So do I need to add 3, 0.4, 3.4, or 2.6? So in the chat real quick, since you guys can use it now, unless you didn't disable it, did you, Mike?
I did, but I'm going to fire it right back up for you. I'll leave it on from now on. Yep.
Okay. Yeah. I might as well. This is
Cool. Yep.
interactive on this. All right. So the question I have is, how much parts per million do I need to add? 3.4, 3.4, or 2.6? I just curious if you can answer in the chat, A, B, C, or D real quick on this. C, C, D, B. Okay, I'm not trying to trick you all. I am just asking, gauging what some may know. And it's looking like some people already know this, okay? So I'm not trying to trick you. So if you don't get it right, don't worry. I'm going to explain how this works, okay? So B, okay. All right. So let me explain how this works then, all right? Because it looks like, oh, what do we get? We got one more, looks like B. Okay. All right, I will explain to you B. All right. I will explain to you how this works, okay? So I wasn't trying to trick you, so don't get flustered, all right? Because flustered with math is where things go downhill, all right? So the correct answer is C here, first off, okay? And let me explain why it is C. So the reason that it is C is there's a thing called chlorine demand here, okay? So chlorine demand, first off, what is chlorine demand? That's the thing. Chlorine demand is the amount of chlorine required by the source water and system. Okay, so what does that mean? All right. So chlorine demand is the amount of chlorine required by your source water and system. Okay. So let me explain how it works. So a water supply has a chlorine demand of 3 parts per million. All right. Milligrams per liter and parts per million are the same thing. What it means is that your water has certain minerals in it, right? There's minerals within your water. We all live, especially if you have wells and even surface water, there's minerals within the water. Well, those minerals react with the chlorine as you add it, and your chlorine residual disappears, right? Meaning if we take a reading, let's say we only add to this water that we're talking about. If we only add 2 milligrams per liter, if we take a residual reading, like get out your colorimeter or your pocket colorimeter and check it, it'll read 0. You won't show any chlorine period in the water. And that's because there's so many minerals in your water that it's eating up your chlorine as you add it. It's kind of like Pac-Man sitting there going num 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 num, right? Eating the chlorine. Well, you have to meet your chlorine demand first before you will see a residual, okay? And the chlorine goes to one of 2 places. It goes to the minerals in your source water as it comes from your well or surface water. And then there's your system. Your system also has its own chlorine demand. If you have old cast iron pipes and stuff like that in your mains, well, that stuff oxidizes parts of the free chlorine in there. So that eats it too. So old pipes eat chlorine. And then the minerals in your water also eat chlorine. They're like Pac-Man going num, 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 num. So this water essentially is going to sit there and keep eating the chlorine until it's full or it's satisfied at 3 parts per million. Okay. So there's an equation that says total dose equals residual plus demand. So when you have a demand and a residual, you have to add them together. So 0.4 plus the 3 will give you the 3.4 parts per million. Okay. So this was not meant to be a trick question. So if you said B or D or whatever, don't get down. Oh, well, it is what it is, right? You didn't even know what chlorine demand was until I probably told you. So that's fine. I'm going to tell you straight up, all of you here, I graduated college with 2 degrees with a 3.96 GPA in 2011. 3.96. That's all A's, right? That's magna cum laude. But the moral of the story is when I got hired to this job, do you think I was a know-it-all? Absolutely. Do you think I failed the test the first time I took it? Absolutely. All right. When I first hired in, I thought I was a hot shot. I knew everything, just because the way I did in college, what are you going to teach me, right? Well, I took the F4 exam and I got a 41% the very first time I ever took it. And that's because I didn't know it, right? So just because if you put B in the chat, oh, well, who cares? You didn't know what it was. You took a shot at it, you guessed. Don't get down on yourselves if you did, all right? It is what it is. I explained it to you because I wanted to just move forward and show you what it is, all right? It's a learning tool. All right, so now that I know it's 3.4 parts per million, I'm going to put it in my equation. Then I'm going to have pounds of Cl2 over my million pounds of H2O, okay? Now I need to find my million pounds of water. It is 300,000 gallons. It's given to me, right? So if I have 300,000 gallons, how do I get that to pounds? Multiply by 8.34. And that's going to get me 2,502,000 pounds. How do I get that to million pounds? We'll divide it by a million. It's going to get me 2.502 million pounds. 2.502. So then you're going to cross multiply, right? So 3.4 divided, well, not divide, multiply by 2.502 is going to give me 8.51 pounds of Cl2. Okay. This thing says how many gallons, but how do I get it to bleach first? How do I get it to bleach? You got to divide by the percent, so 0.12. Is it equal 70.92 pounds? And then how do you get it to gallons? Remember the last step to get the gallons was to divide by how much it weighs. So divide by 10.4. Give me 6.82 gallons of bleach. Hey, that wasn't so bad. All right. So just remember that with chlorine, if you see two of them, you add them together, okay? Now, on fluoride, do not do that. Anyone who's a treatment exam, I'm warning you. On fluoride questions that ask about fluoride, you do not add the two together, okay? Because that's one of the differences between chlorine and fluoride. You don't add them together, right? So don't say I didn't warn you for that, all right? Okay. I want everyone to do, all right. We'll make this last question of the day, okay? Page 70. Man, you guys want to do two? I think we got time to do two more. All right, let's do these. Page 70, I want you to do both. I'll give you, we'll say 5 minutes for both, then we'll go over both, okay? So 5 minutes. These are the last two questions for the day. All right. Last two questions now, okay? So an 18-inch well must be disinfected. You want chlorine residual 125, oh yeah, 125 pounds per million. The depth of the well is 1,000 feet. Well, I'm going to stop there before I get too far into this. I'm going to put my parts per million equals pounds of Cl2 over million pounds of H2O. Okay. All right, so the well's 1,000 feet and the static water level is 200 feet below the top of the casing. Stupid thing. Is below 200 feet of the top of the casing. How many? Okay, so I want to draw this though too, so you can see. So this is my 18-inch well. And we're just going to say that that's 1,000 foot, okay? But the static water level is 200 feet below the top of the casing. So what's that mean? It means it's down here. So what is our true height? Is it 1,000, 200, or 800? It's 800 because this is all just air up here. There's nothing in it. You can't chlorinate the air. So when you do, so the first thing, this is the volume. So the volume equals 0.785 times by 1.5 times by 1.5 times by 800 because it's 1,000 minus 200. Then 748 and 8.34 to get us to pounds, right? Times by 800 times by 7.48 times by 8.34. It's so I got 88,147 pounds. So how do I get that to million pounds? Divided by million. So that's gonna give me 0.088. Now what do? You cross multiply. 0.088 times 1.5, and I get 11 pounds. And that's all it says. It says how many pounds of chlorine, right? So am I done? Yes, I'm done. 11 pounds. That one's pretty straightforward, right? Okay. You are required to add chlorine to your water supply for disinfection. You have determined that your system has chlorine demand of 0.9 and you wish to maintain a residual of 0.5. The flow through your treatment plant is 11 mgd. Assume that's 15% hypochlorite. That weighs 10.4 pounds per gallon. So basically, it just wants to know how many gallons of chemical you should be feeding a day, right? So first off, my residual or my parts per million is 1.4. Got to add them together because demand plus my residual equals pounds of Cl2 over my million pounds of H2O. So I have 11 million gallons. How do you convert that to pounds? Well, to convert gallons to pounds, you multiply by 8.34. So 11 times 8.34 is going to give me 91.74 million pounds. So 91.74 million pounds. And what do? You cross multiply. That gives me 128.44 pounds of Cl2. Now, how do you get that to sodium hypochlorite? Well, you divide by the percent. It's going to be a big number. 128.44. Divide by 0.15. Gives me 856.27 pounds of bleach or sodium hypochlorite, whatever you want to call it. Now, how do I get it to gallons? Well, I got to divide by how many pounds it weighs per gallon. It comes out to 82.33 gallons.